Over the next few videos, we'll be looking at iteration and conditional statements in the form of for loops, while loops, and if statements. You'll use the concepts and syntax that you learned in the previous video, so it's recommended that you watch it before watching this video. Taking advantage of iteration and conditional statements will make you a much more effective programmer, so it's important to learn how and when to use each type. The for loop is used when a set of commands is to be executed a predetermined number of times. In other words, if you know beforehand how many times you want this loop to iterate, then a for loop is a good choice. The basic structure of a for loop is as follows. Typing the word for denotes a keyword that MATLAB recognizes. The next item is something called the loop index. This is a value that changes each time the loop starts over. The way the loop index is changed is dictated by the next item, which is the row vector. This vector is typically a vector containing incrementing integers like 1, 2, 3, 4, 5, and so on. In some cases, you may wish to define this vector having increments other than 1, and in other cases, you may even wish for this vector to begin at a larger number and then decrement until a final smaller value is reached. In all cases, this must be a row vector. What follows in the lines below is the main code you wish to execute. These lines of code will strategically use the looping index to perform dynamic tasks based on your particular application. Finally, once the main code is complete, the end keyword denotes the end of the loop and instructs MATLAB to increment the loop index and return to the top of the main code. Let's see a really basic example of this in action. So, we start with the keyword for and then define our loop index ii. I choose ii because while I seems like a good candidate for an index, I is already defined in MATLAB to be the imaginary number. The next step is to set the loop index equal to a row vector. In this case, we'll make it a very simple vector, 1, 2, 3, 4, 5. Then, in the main code, we'll simply display the loop index ii. We can then use the end keyword to complete the loop. Before we run it, let's think about exactly what to expect. The very first time through the loop index ii is equal to 1, the very first element in the vector. Thus, when the main code is executed, it should display the value 1. As soon as the main code is complete, the loop index increments to the next value in the row vector, this time equal to 2. Then, the main code is executed again, only this time displaying ii should yield a value of 2. This process is repeated until the loop index reaches the end of the row vector, so the last value that should be printed is the value 5. Upon running this for loop, we can see that the result is exactly what we expect. In the command window, the value of the index was printed each time through the loop. Note that the row vector can be any 1 by n vector that you wish. In some cases, you may need the loop to run a very large number of times, in which case a colon operator is handy. For example, we can adjust the original vector to go from 1 to 100. Or in some cases, you may want to use a non-integer value for your index. For example, 1 to 100 in increments of 0.1. One thing to note is that in MATLAB, there's no need to manually increment the loop index in the main code. The loop index is automatically incremented according to your row vector definition. Let's look at another example. A common concept in economics is compounding interest. The idea is that if you put some money into a savings account that grows at a rate of 12% compounded annually, then year upon year your money will grow exponentially since interest accumulates upon interest. We can use a for loop to compute the annual balance in your account based on the initial deposit and the interest rate. The first thing we'll do is to define the initial balance and define how many years we wish to compute. Now, because we actually want to store the balance after each year instead of just seeing the final balance at the end of 30 years, we'll want to create a vector in which to store the annual balances. Using the zeros function, we can create a vector of all zeros of dimension 1 by tf, or 30 in this case. The idea is now to populate this vector element by element as the loop propagates. Now we can actually begin coding the loop. As always, it starts with declaring the type of loop by typing for. Next is to define the loop index. For this loop, we want the new balance to be compounded once per year for 30 years. In other words, we want this loop to run 30 times, each time incrementing the loop index by 1. Thus, the loop index should be equal to a row vector containing the values 1 to 30. However, notice that if we decide to change the variable tf to say 40 years or 50 years, this loop would no longer function properly since it's only programmed to run for 30 years. A better way to define the loop index row vector is to use the length function. Length of bal annual produces the value 30, but it does so in a dynamic way instead of simply typing the number 30. Using the length function returns the length of a 1 by n vector, and since we already defined this vector to have precisely the length of tf, it makes sense to use it in our loop. Now, if we ever want to change the length of the computation, we only need to change the variable tf. For example, if tf is changed to 40 years, then the length of bal annual changes, and then so does the duration of the for loop, as it will now run for 40 iterations. With the for loop now established, we can begin to type the main code. In this example, the variable bal represents the current balance. Since the interest compounds annually at a rate of 12%, we can express the new balance as equal to the previous balance times 1.12. Now, as soon as we update this balance, we want to go ahead and store this updated value into the proper element of our predefined bal annual vector. We can do this by assigning the ith element of the vector bal annual to be equal to the updated balance. And that's it. We can end the loop and the code will return to the top, first setting the loop index to the next value, 2, then redefining the bal variable as the previous balance times 1.12, and then storing the updated value in the ith element, in this case the second element of the bal annual vector. This loop will propagate until the loop index reaches 30, at which point all of the elements of the bal annual vector will have been populated. We can verify the exponential growth of our initial investment by creating a variable representing the year and then plotting the bal annual vector against it. Using a string specifier allows us to view the data as individual data points rather than a continuous plot. Let's look at one final example. In this example, we begin with a 1 by 10 vector v of random variables on the interval from 0 to 1. The goal is to use a for loop to automatically create a new vector that places all of the elements in the random vector in increasing order. The first thing we should do is to create a vector of zeros the same size as the random vector v. We can do this by using the size function or the length function. These lines of code do the same thing. The idea now is to use a for loop to populate this empty vector with the properly ordered elements of v. As always, we start with the for loop declaration. The loop index ii should be equal to a row vector, in this case is values from 1 to the length of v. By using the length function, if we change the length of the random vector, we only need to change it in one place. Then, in the main code, we're going to use the function called min, which finds the minimum value in the given vector. In this case, we also want to know where in the vector the minimum value occurs, so we can use left-handed arguments according to the help function for min that returns both the minimum value and the index in the vector at which the minimum value occurs. We can test this very quickly in the command window. Having the index at which the minimum value occurs is important here because on the next time through the loop, we want to disqualify this minimum value from consideration. One simple way to do this is to set the value to a large number. That way, the next time through the loop, this minimum value will no longer be the minimum value. Of course, the other thing we need to do is to actually store the identified minimum value into our v-ordered vector, into the ith element, like so. And that should really be it. We can end the loop at this point. As your code gets more complicated, it becomes more challenging to visualize what is actually happening within your loop, especially since MATLAB executes code incredibly quickly. Often, it's helpful to do a mental exercise and step through the first couple of iterations of your loop line by line until you're convinced it should do what you expect. In this case, we start at the very beginning of the loop, where I equals 1. So this first time through the loop, everywhere you see I in the main code, you can replace it with 1. The first thing that happens is that we compute the minimum value in v and record the index at which it occurred. Then immediately we disqualify that element so that the next time through the loop, that minimum value is no longer the minimum. We accomplish this by setting the minimum value to a large number. So if we found that the minimum value occurred at the third element in v, then we'll set that third element in v to 100. The next line of code assigns the ith element, in this case the first element, to the minimum value we just found. Then we go back to the top. This time the loop index is 2. We again find the minimum value in the vector v, but remember, the last time through the loop we set the minimum value to 100, so it will no longer be the minimum value. This time we'll get the next largest value in v when we use the min function. Again, we want to disqualify this new minimum value, so we set it equal to 100. Then we store the current minimum value again into the ith, or second element, into the vector v ordered. Hopefully you can see how this process propagates until we reach the end of the vector, at which point all of the elements should be left in increasing order, which we can verify by printing the original random vector as well as the ordered vector to the command window. In the next video, we'll explore the while loop, which is a different type of iterative procedure similar to the for loop, but with different syntax and different applications.